Okay, let's give you guys another example. So let's say we've got a function defined by this power series. In this video, we're going to try and find out values of x for which this whole power series will converge. The values of x which will allow the series to converge also represents the domain for this function. I will elaborate more on this towards the end of the video. This because the values of x for which this series will converge also represents the domain for this function. I will explain towards the end of the video. Well, this power series, when n equals 1, put it into here, it will give you x. When n equals 2, put it into here, put it into here, put it into here, it will then give you this, and so on. It will generate this infinite series. So to find out the values of x for which the series will converge, we would apply this theorem. We would apply this theorem first, and then we would apply this theorem. So to find out, to find out the values of x, the values of x for which this series will converge, we would look at the absolute version of the series. If the absolute version of the series converge, then the original series itself will also converge. So we've seen this in the past. So we would apply this theorem, and then we would apply the ratio test. So remember, with the ratio test, we always compute this value here. You should already know this by now. So this is just revision. So hang on. So to find the values of x for which this series will converge, we would need to look at the absolute version. So we would need to look at the absolute version. If the absolute version converges, then the original series will also converge. Okay, so have a look at the absolute version. So the absolute version, when you look at the absolute version, if you look at this thing here, it's just going to be -1, 1, -1, 1, 1, -1, and so on. So when you take the absolute version of this thing here, you can consider this as the number 1, because -1, take the absolute version, is still 1. 1, take the absolute version of 1, is still 1, and so on. So when you take the absolute value of this whole thing here, you can consider it as this. So now apply the ratio test. So with the ratio test, apply the ratio test. So apply the ratio test. With the ratio test, we always need to compute this value here. If this value is less than 1, we know it's going to converge. If this value here is bigger than 1, it's going to diverge. If it's equal to 1, then it's inconclusive. So we now need to apply the ratio test. So we need to compute this value here. Okay, so hang on. So we got to this stage here. So now we need to apply the ratio test. So the ratio test would be an plus 1 divided by an. So an plus 1 is this thing here, divided by an is the same as multiplying by the reciprocal of an, which would be this thing here. So now tidy this up. That will then give you this, because you can visualize this as x to the power of n times x, and then this will cancel out with this, giving you just x. Well, anyway, this thing here will become this. So now as n tends to infinity, as n tends to infinity, this is just going to be 1. So so the limit will be absolute value of x. So we know that if the absolute value of x is less than 1, we know it's going to converge. If it's greater than 1, we know it's going to diverge. If it equals to 1, it's inconclusive. Okay, if it equals to 1, it's inconclusive. Bear that in mind. I'm going to come back to that later on. So hang on. So we were trying to to find values of x for which this whole series will converge, and it turns out that it will converge if the absolute value of x is less than 1. So if you look at this here, this thing here, this series will converge if the absolute value of x is less than 1, meaning from -1 all the way to 1 here. any values in between, it has to be strictly less than or strictly greater than -1. So all the values in here, if you select x to be anywhere in this interval here, then the whole series will converge. So what that means is the function, the domain for what that means is if if you select any number into here in this interval here, let's say a third. A third is here. If you put a third into this machine here, because a function is like a machine, you put in an input and it will spit out value. It will spit out value because this series will converge. Therefore, it will spit out a number. It will spit out a number. But the thing is, if you put a 2, you see 2 is not in the domain. If you put a 2 into this function here, this thing is going to diverge, meaning that it's not going to be able to spit out a number. It's just going to get bigger and bigger and bigger. It can't spit out a finite number. So 2 is not in the domain. If you put a negative 1.7, say, you see negative 1.7, negative 1.7. If you put it into the machine here, this thing here is just going to diverge. So it can't spit out a number. You see, you can select any number in between -1, because we've established that it will converge if the absolute is less than 1. So you can select anything. So the domain for this thing so far is from -1 to 1. So you can put anything in, any number in between -1 and 1 into this machine, and it will spit out a number. So going back to earlier, we said that if the absolute value of x is less than 1, the whole series will converge. If the absolute value of x is greater than 1, it's going to diverge. So absolute value of x greater than 1, it won't be in our domain. Okay, so but then the thing is, if you look at the ratio test earlier, it says that if it equals to 1, if it equals to precisely 1, then it's inconclusive. But the thing is, it's inconclusive, but we need to check it. I will continue in the next video. It will make sense more in the next video. We will need to take care of this scenario. When it's inconclusive, well, it could converge, or it could still diverge. We need to investigate it when it equals precisely 1. We need to investigate what happens when you input precisely the number 1 and precisely the number -1. Because the ratio test says it's inconclusive. It could converge, it could diverge. So we need to investigate this in the next video.